All right, let me just summarize. This is part 2 of simple matrix functions. We introduced exponential of a, logarithm of a, and we have shown log e to the a is a, and e to the log a is equal to a, and e to the a, e to the b is equal to e to the a plus b if ab is equal to 0. If they commute, ab is equal to ba, and log ab is equal to log a plus log b if log a, log b commute. Now, we shall discuss another important operation on a matrix. That's the trace. Trace of a matrix, we are taking a square matrix, is the sum of the diagonal elements. So trace of A is sum over K, A, K, and K. This is the definition of trace. Trace has important applications, and so let us review its properties. Trace of A is a matrix. Trace A is a number. It's a numerical value associated with that matrix. For example, trace A transpose A transpose ij is AJI by definition. We are taking trace A transpose KK. But if you put KK, it's the same thing. So it is equal to sum over K. So it is the same thing as trace sum over K, A, K, K. So trace A transpose is trace A. So matrix and its transpose have the same. Another thing is, if you multiply a matrix by a scalar, lambda, real or complex, lambda multiplies every element of A. So if you take the trace, it is simply lambda times trace A. That means if you consider lambda A plus mu B, trace A is a matrix, B is a matrix, lambda mu are constants. Trace lambda A plus mu B is lambda trace A plus mu trace B. Therefore, trace is a linear operation. Trace is a linear operation. All right, what about the trace of AB? Trace AB. So it is sum over K, AB, KK. But A and B are matrices, so there's a matrix multiplication implied here. So it is sum over K, sum over J, A, K, J, B, J, K. But I can interchange, these are just elements. So the elements commute, of course. So I can do the sum in this way. This is B, J, K, A, K, J. Or this is the sum J, B, A, J, J, which is just the trace of BA. So trace AB trace AB is equal to trace BA even if A and B do not commute. Do not commute. Even if A and B do not commute, you can change the order under the trace. That's important. Now, I'm erasing this part. We can generalize this. Trace A, instead of B, let me write BC. BC is another matrix. Therefore, this is equal to trace BC and A. So ABC, BCA. So the first one can be put to the last. So here B is the first one. It can be put to the last. So it is equal to trace CBA. So you can cyclically or circularly permute. Circular permutation. Circular permutation. Trace is invariant under circular permutation. But notice that this is not equal to trace, for example, BAC. Because you cannot reach BAC via circular permutation. ABC, BCA, CBA, BAC is not there. So one has to be careful. So circular permutation. Let's write here. Trace ABC is equal to trace BCA is equal to trace CAB. Circular permutation. None of these matrices need to commute with each other, but as long as we keep the circular order, all right, I'm erasing this one. In physics, especially in quantum physics, but also when we do linear algebra in unitary space, that means we can define vectors like this, A, B, and A is a column vector like that. In general, with complex components, A, N, and B is a vector like this, B1 star. It's a So if you call this a matrix M, in general, M, I, J will be A, I, B, J complex conjugate. So trace AB is sum over J, AJ, BJ. And this is nothing but BA. So trace AB, important result for physicists, BA. Let me write it to the top, because here I'm done. Trace AB is equal to BA. Another important relation with trace is if you have a matrix A, and if you make a similarity transformation with U, that means you define a new A tilde, which is U A U minus 1. And if you look at the trace now, trace of A tilde is trace of U A U minus 1. And you see what it does. This is trace circular permutation, trace A U minus 1 U. And this is the unit matrix is equal to trace A. So under a coordinate transformation affected by these, you may have an orthogonal transformation or you may have a unitary transformation, or general similarity transformation, the trace of the matrix is invariant. So it's an important numerical property of a matrix that its trace is invariant. All right. So these are the properties of trace. Let me just say it again. This is the definition. Sum of the diagonal elements. Transpose has the same trace. Lambda times trace is a linear operator. And if you have a bunch of matrices which are not commuting with each other, trace of a certain order is the same thing as that order circularly permuted. This familiar operator with the physicists, its trace is that, and that the trace of a matrix is invariant under similarity transformations. All right, this is about the trace. I'm erasing. All right. Now, with the trace, there is a long list. I will just remind us of trace A. Now, let us look at variations. Variations. For example, if we have A, we can vary A, delta A. And let me just do it with a 2 by 2 matrix, A11, A12, A21, A22, real or complex numbers. This is A. By delta A, I mean all these numbers varied. Delta A11, delta A12, delta A21, delta A22. And for an arbitrary variation, these parameters are small, but they will not be in proportion to these with the same proportionality. So in general, delta A and A will not commute. You will not be able to change delta A. So that means delta A times A is not equal to A times delta A. So this is a different matrix like B, and never mind that its name is delta A. It doesn't commute. All right. Let us now look at certain variations of combinations. Let us look at, for example, delta A minus 1A. A minus 1A is the unit matrix, because this is the inverse. So it is delta I. But what is the variation of I? I is a fixed matrix 1, 0, 0, 0, 1, 0. So it has ones along the diagonal, zeros everywhere. So there is no variation. Delta of I is 0. It has unit matrix has fixed elements. Let us look at here. This is delta of A minus 1 times A plus A minus 1 times delta A. So this is equal to 0. Therefore, delta of A minus 1 times A is equal to minus A minus 1 is 1 over A delta A. And to get this delta A minus 1 from the right, because I have to keep track of right and left because delta A and A are not commuting, I now apply 1 over A and multiply it like this. This A inverse A, so delta A minus 1 is equal to minus 1 over A delta A 1 over A. This looks like, for example, delta 1 over x is minus delta x over x squared. But you can write it there because delta x and x commutes. Here we have matrices and delta A and A do not commute, so we have to keep track of the order. So if you define a delta A, if a certain delta A is given, then delta of A minus 1 is not arbitrary, but it is given like this. So once we have defined delta A, the variation of the inverse matrix is given like that. All right. So let me write here, delta A minus 1 is minus 1 over A delta A 1 over A. I am erasing this part. We are doing variations. Now, I have the function e to the a. So what is the variation of delta e to the a? Well, delta, and here we have it, I plus a square over 2 factorial plus a cubed over 3 factorial, etc. equals delta I is 0, delta of unit matrix, that's 0, plus delta A. Now, how about this one? 1 over 2. I have a squared, so I have delta A plus A delta A. You see, this is not 2 delta A times A or 2A times delta A because they do not commute. And how about the other one? This is 1 over 3 factorial times, I'm affecting, so it is delta A plus A delta A plus A delta A, etc. So it's this is delta e to the a. So this is all this is the third term, and we have infinite terms, and delta is within every power visiting the inside, and they are not commuting, they are not equal. But so that's it. The question is, what if I take the trace? trace delta EA. What's the trace of varied version of the exponential? So it is trace of delta A. Let's go term by term. How about here? Well, circular permutation is allowed. So it is plus 1 over 2 trace delta A plus A delta A, but I can bring it here. So it is 2 times trace delta A. How about here? 1 over 3 factorial. 1 over 3 factorial. So this is A square. So I can put it back here under the trace, circular permutation. Delta is up in front. And here I can put to the back, this one to the back. Delta is, so 3 times trace delta A square, etc. So it goes. So 3 cancels 3 here, leaving 2 factorial. So let me just write it like this. Trace delta A parenthesis I plus A square over 2 factorial, etc. So you see this part is collecting to e to the A again. So it is e to the A. So it is equal to trace delta A e to the A. Now, there is one more thing we can write, and it is this. Trace is a linear operator, and the sum of, so this has an infinite series, so it's a bunch of terms like this, okay? So you take the trace of this term, and then take the trace of the other term, and you add them up. So the sum of the trace is the trace of the sum. So we can also write this thing as delta trace e to the A. So we see that the trace operation and the delta operation are commuting. We can change the order. So let's write this. Let me write this to the top. Delta trace e to the A is equal to trace delta e to the A. That's equal to here trace delta A e to the A. Let me write the variations here. I'm going to erase this. We started with delta EA. It was complicated. And we took the trace. Under the trace, This has a simple relationship. Because without the trace, we could not collect it like this. Let's try it now with the delta of log A. Well, log A is here. That's equal to, here I get the delta A. Then I have 1 over 2 delta A minus I, and from the second one, A minus I delta A. Now the other term, plus 1 over 3 delta A minus I square plus A minus I delta A minus I plus A minus I square delta A. So it is again not simple, because delta A and A is not commuting, and we are already in the third term, and imagine all these terms. It's not it's not possible to write in a compact way. But suppose we take the trace now. Trace of delta log A. So let's do it. Trace delta A minus 1/2. Now, under the trace, I can write like this: 1/2, 2 times the trace of delta A minus I, plus 1 over 3 trace of, now trace of this and trace of that. Suppose I want to have delta A in the front, so in the trace of this I can put it back, and in the trace of this I can put this one to the front. So I have three trace delta A minus I square, etc. It goes. So let's see what happens. So this is trace. Since trace is a linear operator, the sum of the you have a bunch of terms, you are taking the trace. It's the same trace if you first sum them and then take the trace. So this is delta I minus A minus I, here plus A minus I square, etc. It goes. But again, this looks like, if we call this x, for example, this looks like 1 minus x plus x square. It is looks like the expansion of 1 plus x. So let's write it. This is trace delta A under the trace 1 over I plus A minus I. So it is trace delta A 1 over A, or since I can change the order, it doesn't matter, trace 1 over A delta A. So under the trace, it looks like we can operate with it like log of x, delta x, 1 over x. It doesn't matter whether you write it to the right or left, because you have a trace. That trace allows you to do that, whether to write it to the right or to the left. It doesn't matter. So we have found it. So let me write it here. Trace delta log A is the same thing as delta trace log A, and it is trace 1 over A delta A. I don't need to write the other form because now we know circular permutation is allowed. I will erase all this part. So these are important formulas. Namely, under the trace, life simplifies. We can collect the things in front of delta A as e to the A. And this is, if you notice, it's just like the derivative of log x, dx over x. But this is under the trace. I'm erasing all this. So, let me just review again. We had the matrix A, we defined its trace, we discussed the properties of the trace, and then we introduced a variation, delta A. If delta A is given, and delta A is in general not commuting with A, the inverse, the variation of the inverse is fixed, is given like that, once delta A is given. And then we looked at the delta of trace of e to the A and delta of trace of log A. And we also said delta and trace are interchangeable. Now we define something also very important property of a matrix, namely its determinant. Determinant A. And we will define it via Professor Schwinger in a variational statement. Delta log determinant A will be delta trace of log A. You see, log A is a matrix, but trace of it is not a matrix, is a number. And determinant A itself is a number, because the log of, there is no trace here, so the log of that number. And we are, it is defined, this defines determinant A. Now we integrate log determinant A is equal to trace log A plus a constant. Determinant A is defined such that determinant I, the unit matrix, is plus 1. So to determine that constant, let's take A to be I. So this is logarithm of determinant I, which is just 1. So it is log 1, that's 0. That's equal to trace of log I. Log I is 0 because if you put, instead of AI, all the terms are 0. So that's also 0. So the trace of the 0 matrix is 0 plus constant. So the constant is 0. So we have logarithm of determinant A is equal to trace of log A. Or if we exponentiate this, e to the log is simply e to the log determinant a. E to the log is simply, these are inverse functions, so it is determinant a is equal to e to the trace log a. So this is a very important definition and result. Determinant a we defined through this variational statement, and we found determinant a is equal to e to the trace log a. I'm erasing. Determinant a is a number. Trace a is a number. So trace a and determinant a are two important numeric characteristics of a matrix. Let us look at determinant AB. This is equal to e to the trace log AB. Delta of log determinant AB is equal to, let's go from this formula. Where is it? It seems I erased it. Let me write again. Delta of log determinant A was delta of trace of log A, which is trace of, from here, 1 over A delta A. So delta log determinant AB is equal to delta trace log AB. I'm here. Instead of A, I have AB. So it is equal to trace of AB minus 1 times delta AB. Now we will operate with here. AB minus 1 is B minus 1, A minus 1. Remember, in general, A and B are not commuting. So, for example, AB minus 1 times AB is 1. But if you open it up like this, B minus 1, A minus 1, A, B. That's why the order is reversed, because these give 1, and B minus B, that's also 1, so the result is 1. This one is delta A times B plus A times delta B. So this is equal to trace B minus 1, A minus 1, delta A, B plus A delta B. Let's take the trace. With the first one, let me write trace B minus 1, A minus 1, delta A, B, plus trace A minus A is unit matrix, trace B minus 1 delta B. And here you can circularly permute B here, or take this one there. B minus 1 give 1, so this is equal to trace A minus 1 delta A plus trace B minus 1 delta B. I need some space. I move over here. Delta log determinant AB is equal to, this is delta log determinant A, and this is plus delta log determinant B. Now I can erase this part. Which integrates immediately. Log determinant AB is equal to log determinant A plus log determinant B plus constant. A constant number. Now, let us take, for example, A, B, both to be the unit matrix. So determinant I is 1. So log of 1 is 0. 0 is equal to, same here, this is 0 plus constant. So constant is 0. So if this is log determinant AB, log determinant A, so we take the exponential of it, e to the log determinant AB is equal to e to the log determinant A plus log determinant B. But these are not matrices now. Determinant A is a number, determinant B is a number. So this is just like e to the x plus y. So it is e to the x times e to the y. So this is e to the log determinant A, e to the log determinant B. And this is AB is equal to, determinant AB, determinant AB is equal to determinant A, determinant B. In fact, all right. This is a very important result, determinant A. So with determinants, we have two important results. I'm erasing some part. Let me erase this. Determinant AB is equal to determinant A times determinant B. So these are two very important properties of the determinants. Determinant A is e to the trace log A, and determinant AB is equal to determinant A, determinant B. So one can derive many properties of determinants from using these two relations. For example, determinant A, AB, determinant AB. I am using this these two. Determinant AB is equal to e to the trace log AB is equal to determinant A, which is e to the trace log A, times determinant B, e to the trace log B. Now, trace log A is a matrix. Trace log A is a number. Trace log B is a number. So these are numbers. So this is simply e to the trace log A plus trace log B. So if you just take the log of these, you obtain trace log AB is equal to trace log A plus trace log B. Even if log A and log B do not commute. Log A, log B not equal to 0. That means here we could not write the relation log AB was not equal to log A plus log B, but their trace is equal. Trace log AB is equal to trace log A, trace log B. All right, here I want to indicate a point. One immediate, all right, so this doesn't hold as it is, but it holds under the trace. It immediately brings to question if AB is not, if A and B do not commute, then e to the A, e to the B is not equal to e to the A plus B. But the immediate question that comes to mind is trace e to the A, e to the B. Is this equal to e to the trace of e to the A plus B? The answer to that is no. It turns out that trace e to the A, e to the B is there is an inequality. It is larger than trace e to the A plus B, and this is the, you can look it up from, you can Google it or look from books. Golden Thompson inequality. So although this relation holds for the log, namely under the, even if they do not commute under the trace, we can write it like that. For the functions e to the A, e to the B, you cannot collect them e to the A plus B even under the trace. Even under the trace, they will not be equal in general, but there is an inequality. Okay.